Hi, everybody. Welcome. It's the top of the hour. My name is Diana Sinton. I'm the Executive Director of UCGIS, and I welcome you to the first in our series of presentations, our webinars for the year 2019. The second half of our 2018-2019 webinar series. We are going to start this webinar in just another minute. Attendees are continuing to arrive as we speak. As a reminder, this session is being recorded and you'll be provided with a link by tomorrow. When you no later than tomorrow, you'll be able to get a link to this. And I feel free to share that with other people within the UCGIS community. It'll be up on the UCGIS YouTube channel. And as another reminder, your microphones will remain muted throughout this webinar. If you have questions for our presenter, for Yingjie, and I hope that you do, please type them in the question space. And then at the conclusion of his presentation, my colleague Paolo Raposo and I will be able to share those questions with Yingjie for him to respond to. So let's see. I'm going to start this in just one more moment or so while we allow other people to continue to log on right now. Okay, I think it's time we can go get started. So I am very happy to share with you this presentation today by one of our UCGIS colleagues, Yingjie from University at Buffalo. And Yingjie, I am going to turn over the presentation to you now.
Okay, thank you, Diana. Okay, so Diana, can you see my screen?
I can see your screen. It's not in presentation mode yet.
Okay.
Yep. There we go.
Okay, so is it now in presentation mode?
Correct.
Okay, great. Wonderful. Okay, everyone, good afternoon. Today, let's explore geotext data. So nowadays, many different types of geodata have become available. So there are global events data, which tell us the location and the time of events happened throughout the world. There are international flight data, which enable us to study the connections among cities. There are also social media data, which allow us to understand the behaviors and activities of people at different locations. So among these many different types of data, there is one type that link geographical locations with natural language texts. Examples of this geotext data include geotagged tweets. So we have the locations of these tweets, and we also have the textual content of these tweets. And geotagged housing posts. So we have the location of the advertised housing property. And meanwhile, we also have a textual description about this property. And also news articles that contain place names. So one uniqueness about geotext data is that we have texts instead of numbers attached to locations. This can be differentiated from other geodata, such as local temperature data, where we have numeric measurements attached to different locations. So for geotext data, we have a sentence or maybe a paragraph or even a whole article attached to one location. So this uniqueness brings challenges because generally it is more difficult to automatically process these texts to interpret their semantics. But on the other side, it also provides great opportunities for studying human-place interactions. So we can consider texts as a proxies of human experiences. And by looking into texts and the locations together, we can enhance our understanding on how humans actually interact with places. So in this presentation, I will share 3 studies that look into geotext data to understand human-place interactions. And particularly, I will be talking about place names, place relations, and also place sentiments. So let's look at place names first. People refer to places by their names. And from a perspective of space and place, the birth of a place name signifies the important moment when people explicitly integrate human experience with space. But people do not always refer to places by their official names. Local place names are frequently used by people but may not be officially recorded. Examples of these local place names include K-Town in Los Angeles, which refers to Koreatown, or Dumbo in New York, which refers to down under the Manhattan Bridge overpass. Sometimes the same local place name may be used in different cities, referring to different geographic areas. So there is Soho in London, which refers to the west end of London, Soho in New York, which refers to south of Houston Street, and Soho in Los Angeles, which refers to South Hollywood. Collecting information about these local place names has important meaning. In disaster response, residents in the disaster-affected areas may use local place names in their phone calls, in their short text messages, or in their social media posts. And if a computer system can automatically recognize these local place names and geolocate them, we may be able to reach those people who need help more quickly. For public participation in GIS, the participating residents may also use local place names to refer to neighborhoods or to refer to other local areas. And if a GIS can recognize and understand these local place names, it can facilitate the discussion process. So in this work, we propose to extract local place names from geotagged housing posts published on local-oriented websites such as Craigslist. And we think there are several advantages in using geotagged housing posts for this task. Firstly, these geotagged housing posts, they indeed contain local place names. So here is an example from Los Angeles, and as you can see, it indeed contains some local place names such as K-Town, such as USC. Secondly, nowadays, housing posts are widely available in many different cities and towns. So methods developed based on this data set can be generalized to many different locations. And finally, because of these housing posts, they are being constantly posted, we can also use them to identify those recently created local place names. So we developed a 2-stage framework integrating natural language processing and geospatial clustering. So the input of our framework is geotagged housing posts. So we have the locations, and we also have the textual descriptions of these housing posts. And our framework has 2 stages. In the first stage, we look into the textual content of these posts, and we try to extract place name candidates. And in the second stage, we look into the locations associated with these place name candidates, and we try to differentiate true place names from false place names. Eventually, the output contains a list of identified place names, and also their rough spatial footprints. So let's look at these two stages in more detail. In the first stage, we use a combination of four named entity recognition tools to extract place name candidates from the textual content of these housing posts. Specifically, we use the Spacy NER, Stanford NER, two of the Shelf NER tools. We also used a caseless Stanford NER to handle some of the irregular upper and lower cases in these housing posts. We also retrained a Stanford NER using a Twitter dataset because it contains the language that is more similar to the style posted in these housing posts. So each of these NER tools will extract multiple place name candidates from one housing post. Here is an example of applying the Stanford NER to a housing post. And as you can see, place names such as Lower Manhattan, Soho, Tribeca, and East Village, they are identified. But it also misses, for example, FIDI, which refers to financial district, and LES here. So we take a strategy of union, which basically combines the output from these four NER tools. And then we associate each place name candidate with the locations of the different housing posts that mention this place name candidate. Then in the second stage, we perform geospatial clustering on these locations associated with place name candidates. And our goal is to differentiate true place names from false place names. The reason we need to do this is because in the output of the first stage, it also contains some false positives. So some phrases which look like place names but are not. For example, the phrase central AC, clearly it is not a place name, but it is included because grammatically it looks like, for example, central LA, which is a true place name. In order to differentiate these two types of phrases, we consider it as a geospatial clustering problem. And the intuition is that for a true place name, the points associated with it are more likely to cluster within a geographic area. Whereas for a false place name, such as Central AC, the points associated with it can be scattered in the study area because almost any location can say that they have a Central AC. But the challenge is that for these true place names, they can refer to areas in different geographic scales. So they can refer to points of interest. They can refer to neighborhoods. They can refer to sub-city regions. So if we simply use a single distance threshold to perform this clustering process, we will not be able to recognize all of these place names referring to geographic areas in different scales. To address this issue, we use an approach called a scale structure identification, originally proposed by Yahoo Labs and UC Berkeley when they were analyzing Flickr data. So the general idea of SSI is that it will perform multi-scale clustering simultaneously. And it starts by defining a sequence of distance thresholds which gradually increase. And at each distance threshold, SSI will try to connect the points whose distances are smaller than this distance threshold. So if you look at the points, the 4 points at the corner of the slide, so with the increase of the distance threshold, we may first see, for example, these 2 points be connected together. And then if we continue to increase the distance threshold, we will see these 3 points connected together. And eventually, if we increase the distance threshold large enough, all points will be connected together and form one connected component. So what SSI does is that at different distance thresholds, it will try to calculate the entropy and then eventually sum up all of these entropies at these different distance thresholds. So here is an illustration for this process. So for a true place name such as K-Town, the points associated with it will quickly be connected together and eventually form one connected component as we gradually increase the distance threshold. But for a false place name like this, and then with the increase of the distance threshold, the points will be connected together only slowly. So if we calculate the entropy sum for both of the two cases, the true place name will have a relatively small entropy sum compared with the false place name. So then what we can do is that we can basically apply SSI to the place name candidates from the first stage, and then we rank them based on their SSI scores from small to large, and then eventually we decide the threshold and then return the place names whose SSI scores are smaller than the distance threshold. So that is great, but our pilot experiments noticed some limitations of this approach when the number of points associated with a place name candidate is small. So here I have two true place names, place A and place B. Both of them, their points become one connected component as we increase the distance threshold. But place A is associated with 4 points, place B is associated with 6 points. So if we directly calculate their entropy sum, we will get quite different values. This is not much a problem for the initial paper because in their work, they were analyzing locations associated with Flickr tags. And in their case, each Flickr tag is associated with about 200 locations. So the difference at that scale is quite small. To address this issue, we added a small normalization component, which is basically just the square root of the total number of points associated with each place name candidate. And this square root is decided in an empirical way, and I will show that in my experiment later. So after this normalization, the SSI scores of these two place names becomes more similar. So to test the effectiveness of our approach, we collected geotagged housing posts for 6 different cities. So New York, Los Angeles, Chicago, 3 large cities, Richmond, Boise, and Spokane, 3 relatively small cities. And we collected geotagged housing posts for 3 months and a half. And we apply our 2-stage framework to this to each city. And for each city, we extracted a list of place names and their rough spatial footprints. So how good is our result? In order to evaluate the performance of our model, we compare it with 6 baselines. But before we can do that, we need to somehow get a ground truth data set. So we randomly selected 20 geotagged housing posts from each city. So in total, we have 120 housing posts. And then we have 3 human annotators who manually looked into these housing posts and annotated the mentioned place names. So with this human annotated data set as the ground truth, we then use 2 metrics, precision and recall, to measure the performance of these different models. So basically, precision measures the percentage of the correctly extracted place names among all the place names extracted by a model. And the recall measures the percentage of the correctly extracted place names among all the place names that should be extracted. And we compared our approach with DBpedia Spotlight, OpenCalais, 2 NER tools based on an external knowledge base. We also compared our approach with just using the first stage, so just the 4 NER tools, as well as the original SSI, as well as 2 different variants of SSI. Eventually, as you can see, our approach which is the blue curve, achieves the best performance among these several approaches. In addition, we also look into how the place names extracted by our approach compared with the existing place names in existing gazetteers. Because the ultimate goal of our approach is to enrich the gazetteers. So we want to see if our approach can indeed extract some local place names that are not yet recorded in these gazetteers. So we compared our data with Foursquare, with GeoNames, with TGN, and also with Who's On First. And compared with Foursquare, our approach only extracted a handful of new place names. So Foursquare is a location-based social media, and it allows users to create and contribute new place names if they couldn't find such a place name in the database. So it indeed has quite a comprehensive database of place names. But the data of Foursquare is a commercial product, so it has its usage limitations. And for the other three publicly available gazetteers, our approach indeed extract quite some new place names. So conclusion for the first part, in this work, we propose a two-stage framework for extracting local place names from geotagged housing posts. And this framework can be applied to geotagged housing posts in other geographic areas, and can also extract those more recently created place names. And these extracted local place names can help GIS and also other computational systems to capture the ways people refer to places and to contribute to various applications. Okay, so now we have talked about place names. Let's look into place relations. Places can be related for a variety of reasons. There are urban actors, such as persons or companies who may travel or conduct business from one city to another. Or there can be events or intercity policies that involve multiple cities together. Place relations in human minds are shaped by the information we obtained from news, from books, from movies, from personal experiences, and from many others. In this work, we examine the relatedness of cities through news articles. And we want to find out how cities are related to each other in the content of news articles. And specifically, we are looking into the semantic topics of this relatedness. So whether two cities are related together because of public policies or because of environmental issues. And also the temporal dynamics of the city relatedness. So how their relatedness change over the years. To do so, we leverage city co-occurrence and topic modeling. So the core idea is that we consider the co-occurrence of two cities in the same news article as evidence to establish a link between these two cities. And then we use topic modeling to extract the topic of the news article and use these topics to annotate the relatedness between the mentioned cities. So based on this core idea, we develop a machine learning workflow. So in the training stage, we use a set of human labeled news articles. So basically each news article is labeled with a set of topics. And we use this data set to train an LLDA model, which is labeled latent directly allocation model. So this trained LLDA model will be able to look into a news article and automatically identify the relevant topics discussed in this news article. And once the LLDA model is trained, we can then organize the news articles in our dataset by years. right? We can organize it as 2013, 2014, 15, so different years. And then we input it into the trained LLDA model. And the trained LLDA model will calculate topic scores for each news article with regard to the trained topics, and then identify a threshold, eventually return the topics whose score are higher than the defined threshold. And these extracted topics will be used to annotate the relatedness of the cities that co-occur in these news articles. With this workflow, we did a case study. So we retrieved more than 500,000 news articles from the US edition of The Guardian, which cover the top 100 cities in the contiguous US. And the dataset covers from the year 2006 to 2015. So in total, 10 years. And we apply our method to this dataset, and then we extract the city relatedness under these different semantic topics and also in these different years. And once we get this individual city relatedness, we can then aggregate them in different ways. So if we aggregate them based on the different semantic topics, we get city networks under different topics. So here are two examples of city networks under the topic of politics and also under the topic of science and technology. As you can see, the same city can perform very different roles under different topics. So under the topic of politics, we see cities such as New York City and Washington, DC, which are playing very important roles. But under the topic of science and technology, well, we also see New York City and Washington, DC. But meanwhile, we also see cities such as San Francisco and Seattle that are playing a much more important roles under this topic than their roles under politics. And if we zoom into one particular city pair, we can look at the major topics of their relatedness and how such relatedness change over the years. So if we look at New York City and Washington, DC, we can see the major topics between their relatedness is about politics and also conflicts, war, and protests. But if we look at, for example, Los Angeles and New Orleans, and then we see a different picture. So the major topics for the interactions of these two cities are about environment and disaster. So you may have already noticed that there is a peak for these two cities in 2014. And with curiosity, we read some of the news articles about these two cities. And we find that there is this 100 resilient cities program, which basically helps cities become more resilient in the face of natural disasters. And both Los Angeles and New Orleans were enrolled in this program in 2014. So there were multiple news articles reporting this event. So conclusions for the second part. In this work, we propose a method for reading large numbers of news articles and extract city relatedness based on the content of news. City relatedness can have different strengths under different topics and can also change over time. And the relatedness from news can be combined with those derived from other media to understand the information that shape our thinking, that shape the place relations in our minds. So now we have discussed the place names and place relations, and let's look into place sentiments. People develop feelings and sentiments toward places. Generally, after we have lived in a neighborhood for some time, we begin to develop some feelings toward it. Maybe some aspects we are quite happy about, maybe some other aspects we feel they can be improved. So the sentiments of people toward neighborhoods can reflect their satisfactions with their living environments. However, collecting data on the sentiments of people toward the neighborhood can be difficult. So we can use surveys or face-to-face interviews to ask people about their sentiments toward their neighborhoods. But it can be challenging to interview, for example, hundreds or even thousands of people. In recent years, there is an emergence of neighborhood review websites. So basically on those websites, people can rate and also comment on these neighborhoods. So here is a screenshot from niche.com. And as you can see, people can say, I want to rate this neighborhood as a 4-star, and then write some comment here. So in this work, we propose to analyze these online neighborhood reviews to understand the sentiments of people toward their neighborhoods. And such a study has several values in quality of life, in urban planning, and possibly others. While we can directly use the single numeric rating of a reviewer, we noticed that people often provide owning a single overall rating, but actually comment on more than one aspect. So here is an example review. So you can see the reviewer give a 4-star of the neighborhood and then wrote, this neighborhood is close to a lot of restaurants and stores. However, I don't feel very safe as there are sometimes suspicious persons walking around. So if we look at the content, we can see that the reviewer is talking about 2 aspects, right? So one aspect about restaurants and stores, and another aspect about safety of the neighborhood. So our question is, can we somehow decompose this single overall rating to aspect-specific rating to obtain finer information about people's sentiments towards these different aspects? So we divide this into 2 subtasks. In the first subtask, we try to identify the semantic topics from these reviews. So we want to find out what are people talking about? What do they care about their neighborhoods? In the second task, we were looking into the sentiments. So what are the sentiments of people toward these aspects? And we experimented with multiple methods for these 2 subtasks. So for semantics, we tried LDA, latent direct allocation, and also a multi-grain LDA approach. For sentiments, we tried a naive approach, lexicon approach, and also latent aspect rating analysis. So let's look at these 2 subtasks. For the first task, we used LDA, which is an unsupervised approach for topic modeling that can automatically identify topics from textual documents. But LDA will require an input parameter K, that is basically how many topics are there in the dataset. And for MGLDA, it is a variant of LDA proposed specifically for analyzing online reviews of products, so initially for these online shopping websites. The major difference between MGLDA and LDA is that MGLDA differentiates global topics, which it considers as noise topics, so topics specifically associated with some products, and also local topics, so readable aspects shared by different products. And then for the sentiment part, we tried 3 different approaches. So for the naive approach, basically we assume that the reviewer has the same rating as the overall rating toward all the discussed aspects. For lexicon approach, we use an external sentiment lexicon, so with keywords and with the sentiment words and also their sentiment scores. And we use these words to quantify the sentiments of the reviewer toward these different aspects. For LARA, it basically trains a latent aspect regression model without using an external sentiment lexicon. So Lara assumes that the reviewer has latent aspect-specific ratings in his or her mind, and the observed overall rating follows a normal distribution with mean as the weighted average of the aspect-specific ratings and the standard deviation delta here. So with the identified methods, we then did a case study in which we retrieved 7,673 online neighborhood reviews about New York City. And this review data covers 233 neighborhoods in New York. And here is a simple visualization of the overall ratings spatially jointed to the neighborhoods. And with this data set, we first try to identify the semantic topics. So the topics that people are talking about these neighborhoods. And we tried LDA first. And for the value of K, we tested K from 2 to 10 using 4 existing metrics. And we also manually examined the clustered result for some of these K values. And eventually we found out that K equals to 8 produces relatively clear topics. And as you can see, these topics are related to crime and safety, to community friendliness, to life convenience, to transportation convenience, housing conditions, and so forth. For MGLDA, we set the K local equals to 8 in order to make it comparable with LDA. And for the number of noise topics, we set it as 20 as recommended by its authors. However, the result of MGLDA contains quite some mixed topics. So for example, the topic of safety seems to be mixed with this topic and also this topic. And also we see a topic like this, which is hard to interpret. So based on this result, we eventually choose the topics identified by LDA. Then in the second stage, we look into the sentiments and we try to use the 3 approaches we identified for the sentiment analysis. And each of these approaches will output a result with aspect-specific ratings. So eventually we have 3 sets of results of sentiment analysis. But how good are they? In order to evaluate the result, we conducted an experiment using Amnon's mechanical Turk. So we randomly selected 1,000 reviews from the dataset, and then each review is rated by 5 different AMT users. So here is the interface that we used to conduct the AMT experiment. So each AMT user will be able to look into a review like this, and also the overall rating of the author. And then the AMT user can check which aspect this review has talked about, and then give a rating about this aspect. In order to increase the quality of the data collected from the AMT platform, we also added an attention test. So basically, we ask the AMT users to always check this option and select 3.5 star. And we only use those results that pass the attention test. So eventually, for each review, we take a strategy of majority vote. So we use the aspects identified by at least 3 AMT users. And then we average their score to get the ground truth rating score for that aspect for that review. So with this ground truth dataset prepared, we then compare our 3 sets of results from these 3 models with the ground truth using the metric of average rating loss. So basically, what average rating loss measures is that it compares the difference between the labeled rating and also the predicted rating, and then calculate the sum and average of the absolute difference. So in this figure, each row represents the rating distribution of the different aspects. And each column here represents a method. And here the first column represents the human annotation result. And these numbers represent the ARL scores. So as you can see, overall, LARA has the lowest ARL scores compared with the other two approaches. But another interesting finding we also noticed is that overall, the naive approach performs better than the lexicon approach. So we think there may be two reasons for this result. One is that the lexicon approach uses a sentiment lexicon which is derived from another corpus, which may not fit the words used for neighborhood reviews. But also we noticed that such a lexicon cannot capture individual differences when they are expressing sentiments. So what we notice is that different users may use the same word to express different sentiments. So one user may say good to express 5-star, and another person may say good to express 3-star. So the sentiment scores in a lexicon just cannot capture those individual differences. So eventually, if we simply assume that the overall rating is the same as these individual ratings, we actually get a better performance than an external lexicon approach. So with the derived aspect-specific rating for each review, we can now aggregate them to get the average aspect-specific rating for different aspects for these neighborhoods. So here is the result that we get for the 8 aspects about the neighborhoods in New York City. And on the left side, I also put the overall rating for these neighborhoods for comparison. So as you can see, if you compare these aspect-specific ratings to the overall rating, we indeed get some new information. So if we look at the overall rating, seems like most neighborhoods, they get an average score between 3-star to 4-star, so quite average among these 5 stars. But if we look at these aspect-specific ratings, it seems that people in New York City are quite happy about, for example, community friendliness, its cultural diversity, life convenience, and transportation convenience. And it also seems like people are not very happy about local weather, the employment opportunity, and housing conditions. So this type of information, they are hidden and are not directly seen from the overall rating. Another thing we also noticed is that there seems to be some clustering of high ratings and clustering of low ratings. So to verify this, we performed global Morris eye on this each aspect-specific sentiment. And the result shows that for 6 aspects, there is indeed a statistically significant spatial autocorrelation in these aspects. So this result shows that for aspects such as crime and safety, such as life convenience, nearby neighborhoods are indeed likely to be perceived similarly by people. We also did a further study to compare the sentiments with some socioeconomic data. And the motivation we do this is because the sentiments of people, essentially it's subjective. So we are curious about how those subjective sentiments are similar or different from those more objective socioeconomic data. To do so, we used a variety of socioeconomic data. So we used crime records from NYPD. We used POI data from Foursquare, bus and subway data from MTA, race and unemployment data from ACS, and also housing price from Department of Finance. And we performed correlation analysis. We found that for crime and safety, there is a statistically significant and negative correlation between the perceived happiness, between the happiness and also the count of the crime. So basically, more crimes, low happiness. And for life convenience, we find a statistically significant positive correlation. So if a neighborhood contains more and more POIs and with higher density, and then people generally tend to be happy. But we also noticed that for the other 4 aspects, there are no statistically significant correlation. So why do these insignificant or weak correlations happen? So firstly, there is this representative issue. So like many other web-based data, the online neighborhood reviews, they were contributed by users who may not represent all the residents in the neighborhoods. Secondly, there is individual preferences and also subjective preferences and individual differences. So basically, for example, for the same condition, for the same housing, a low housing price for one family can be a high housing price for another family. And for cultural diversity, people may have varied opinions on what can be considered as diverse. There are also issues which are not captured by socioeconomic data, but are discussed by people in the reviews. So for example, for transportation, our data about the bus stops, subway routes, they basically capture travel convenience. So how easy it is for a person to travel from one location to another location. But in the reviews, we also noticed that people are talking about the reliability of bus schedules. So how often the bus got late, and also how rude the bus drivers are. And for the employment, we noticed that people not only care about being employed, but also care about the quality of jobs. So some people wrote that they do have a job, but it's just their job is working in a fast food restaurant. So they are not very happy about that. So conclusions for the third part. In this work, we look into the sentiments of people toward the neighborhoods. And these sentiments reflect people's satisfactions with their living environments. And we experimented with multiple models, and we identified the effective models for extracting semantic topics and aspect-specific sentiments. And these place sentiments, they are essentially subjective, and they may not necessarily correlate with those more objective socioeconomic data, but they may also reveal issues which are not yet captured. So a summary. In this presentation, I talked about geotext data. Basically, it links geographical locations with texts. And this type of data provides unique opportunities for studying human-place interactions. Particularly, I talked about place names, so how people refer to places in their everyday life. And we also discussed place relations, how places can be related to each other in the minds of people. And finally, we discussed how people feel about places and also different aspects of places. So these and other studies can contribute to better understanding on human-place interactions and can be used in disaster response, urban planning, and other applications that can benefit our society. So that's it. Thank you very much.
Yingjie, thank you very much for that presentation.
Thank you, Diana.
That was really interesting, and I'm going to have a few questions now. I'm going to turn this over to my colleague, Paolo Raposo, who is the UCGIS Communications Chair and also a professor at University of Tennessee. Paolo, it's yours. Can you hear me, Paolo? Can you hear me now? I can't hear Paolo. But Yingjie, while Paolo's working on his microphone, we had someone who has asked about what different, let's see, earlier in the presentation was wondering about the range of tools and language that you have used in this. Is that a straightforward question to answer?
Does that mean, so I guess does that mean the place name part, the first part about place names, the tools?
Yeah, they weren't specific about that.
Okay, so I guess I can talk a bit about that. So for extracting the local place names, we used a number of NER, named entity recognition tools. So SPACY NER, Stanford NER, and also 2 variants of Stanford NER. So these tools, basically what they can do is that they can just look into an unstructured text, so just any text, and identify named entities. So they can identify locations, they can identify persons, they can identify organizations. But specifically, we focused on the locations part of these tools. And these tools, they are also openly available. You can directly use them for free. For the geospatial clustering part, we used the tool called scale structure identification. It's an algorithm initially proposed in a previous paper by another research group from UC Berkeley and also from Yahoo Labs. In their original paper, they didn't provide a code implementation, but they listed the algorithm there. So in this work, we actually implemented their tool. And I also share this tool on my GitHub website. So if you are interested in this tool, send me an email and I can send you the link of this tool.
That's great. Yeah, let's remind people that you have some of your tools available on a GitHub site. That's super. There's a question here about...
Can you hear me now, guys?
Yes, Paolo, we can hear you.
I don't know what that was all about. Okay.
Well, no worries. I'm going to turn it over to you now, Paolo.
Okay, apologies for the technical hiccup. Yay. Cool, okay, so Rasta Farzan, sorry if I'm pronouncing that incorrectly, is asking, do you have any thoughts on how to use your methods to identify some of the unjustly biased sentiments towards neighborhoods, particularly in marginalized communities that are frequently associated with negative sentiments that can harm their communities, such as unjust fear or safety that influences some of shared economy decisions?
That is an excellent question. So it is definitely possible to use the approach that we proposed here to link it with the demographic information about its neighborhoods and to further link the sentiments with the demographic characteristics of these neighborhoods. So in our work, we haven't done that. But if we can integrate, for example, the demographic information further from ACS, from US Census, and maybe even adding some, I would even prefer to add some offline surveys and also interviews to further complement both the online reviews and also the surveys and face-to-face interviews to get a more comprehensive sentiments towards these neighborhoods and also link it to these demographic features. I think that will be very interesting to look into and a fantastic research topic. Hello.
Got it. Okay, so Tom McKay asks, I'm wondering where shapefiles for New York City neighborhoods were accessed from, and if there's any neighborhood shapefiles for other cities. I'm going to guess you got that from New York City themselves. They're very open with their data.
That's a very good question. So for the boundaries of the neighborhoods, there are no commonly agreed boundaries. So what we got is that we use the shapefile provided by niche, so by niche.com. And I think they got it from PDR City. So I do have the link of their original data source. So I can also send that information to you. But generally, I think it may be better to use the neighborhoods that specifically fit your particular study, because the boundaries, they can vary from different perspectives.
Well, that leads into Chaya Nika Singh's question, which is, how are you defining neighborhoods?
That is a fantastic question. So yes, so neighborhoods in this presentation, I was not trying to define it, giving it a crisp definition. So basically, in this case, we use the same neighborhoods considered by niche by the neighborhood review website, because this is more from a data analysis perspective, because we are going to analyze the reviews. So we adopt the same consideration of neighborhoods. But the definition of neighborhoods can really varies. So you may define it based on, for example, some the actual activity areas of people, or you may define it based on some, for example, some local organizations. So there can be different ways to define the boundaries of neighborhood. So I'm not sure if that is satisfying, but feel free to send me an email and we can discuss more.
Cool. Okay. Song Gao is curious, did you find any limitations for the text-based sentiment extraction?
So I think the limitations is probably more from the, I would say is probably more from, so first of all, I think there are two levels of limitations. So one level is in the data itself. So because the data, they are contributed from the web. So although it's relatively easy for us to collect a relatively large number of reviews, the result, this data can still be biased. So they can still not represent the entire residents population in this neighborhood well. So this is more from a data perspective. And I think there is also a limitation from the tools perspective. So in terms of the sentiment analysis tool we use, and also the semantic topic identification tool, LDA, we use to look into this data, because it is really challenging to process this unstructured text in a perfectly accurate manner. So there are still some of the potential topics that could be identified, but are not perfectly identified by these tools. And the sentiment decomposed by Lara is also not perfect and can still use some improvement. So there are limitations, absolutely. And thank you very much for the question.
I've got a question, Yingjie. When you're
Paulo,
spatially, oh, hello.
Paulo, can you? This will be our last. This will be our last question, just because we're at the top of the hour. The other question,
then I am going to cede to someone else's question then.
Yeah.
All right. Then, and we've got two questions. Oh no, how do I pick?
Actually, this is a great opportunity. We have a number of questions here that we have not been able to answer, and because of time limitations, we're not going to be able to do that right now, unfortunately. But what we're going to do is gather these questions we haven't been able to answer, and we'll email them to Yingjie and ask him to follow up with responses, and I will distribute them to the full audience here, so we have the benefit of everyone learning about these additional questions and responses.
That works.
Yeah, sorry I have to do that just because of other time limitations right now, but I'd like to thank you very much, Yingjie, for this presentation today.
Thank you, Dan. Thank you, Paulo.
And we look forward to following the work that you're doing. Everyone, as I'll take this opportunity too. Yingjie is going to be a panelist at one of our at our 2019 symposium on geospatial humanities. So again, the 2019 UCGIS symposium that's being held in June in Washington, D.C. Has its focus on the geospatial humanities, and you'll be able to hear Yingjie as one of the panelists during that, and many other prominent speakers along with him. So with that, I'm going to wrap this up today. Everyone, again, thank you for your attention, and I will be forwarding the link to the recording that you can feel free to distribute by tomorrow. So thanks, everyone.
Okay, thank you, everyone.
All right, bye-bye.
Bye-bye.